Section 13.10 or 1310 is called voltage and frequency induced in the rotor. And what we're going to do, we're going to take our first two equations for synchronous speed and for slip, and we're also going to add two more equations. And there's one more equation, and when I look at chapter 13, I always teach this class telling the students that if you can know these five equations and understand what they mean, you have a good fundamental understanding of how an AC induction motor works, okay? And so the equations that we're going to add to 1 and 2 is this equation 13.3 and 13.4, and I'll put those up here right now so we can all look at those, okay? So 13.3 says that the frequency of the voltage and current in the rotor in hertz is equal to the slip times the frequency of the source that's connected to the stator. Okay, so one way I like to remember that is at startup, the slip is 1. So 1 times whatever the frequency is in the stator equals the rotor at startup. Okay, and then the other one says that the voltage induced in the rotor, E sub 2, is equal to the slip times the voltage or open circuit voltage induced in the rotor when at rest. Now there's a little explanation there. He says in a cage motor, open circuit voltage EOC is the voltage that would be induced if the rotor bars were disconnected from the end rings. Okay, so then he gives a special case about a wound rotor motor. You know, that's a different calculation, but it said it should be noted that equation 13.3 always holds true, but 13.4 is valid only if the revolving flux, expressed in Webers, remains absolutely constant. However, between 0 and full load, the actual value of E sub 2 is only slightly less than the value given by the equation. Okay, so why don't we just add this to it, and we got it covered, and we can use it just to our liking. And so we've got 4 equations, and like I was telling you, there are 5 equations, and I could go ahead and find the 5th one while I'm here. It's 13.5 is full load current estimation formula, and I'll write that down here. And if I know all of these, then I have a really good fundamental equation or understanding of how an induction motor works, okay? So there's our 5 equations. Now there's a lot of other equations, but those are the 5 that I'd like for you to know, okay? I'd like for you to be able to just know those, plant them in your brain, and so forth. Now, what we're going to do here, we're going to work a problem, and I guess I'll just keep rambling on here, and we'll go ahead and work this problem. It's a great problem. It is example 13-3. And 13-3 says that we have a 6-pole motor, and it is excited by a 3-phase 60 hertz source, and he wants us to calculate the frequency of the rotor current, the frequency under the rotor current at standstill at 500 RPMs in the same direction as the field, at 500 RPMs in the opposite direction of the field, and the motor turning at 2000 RPMs in the same direction as the rotating field. Okay, now most of these problems, the first thing that you're going to do, and we'll walk through each one of these, we'll start at A here, and I'll try to work that in that little space. But at A, well, what I was going to say is most of the time you really need to start by calculating the synchronous speed with these problems. So that is equation 13.1, 6 poles, 7,200 on the numerator divided by 6 will give us 1,200 RPMs. That is the speed of the rotating magnetic field that is happening in that stator right there, okay? Because it is connected to these 3 phases of electricity coming into the junction box there, okay? So, synchronous speed is 1,200. Now, what I'd like to know is what's the frequency of the rotor current under the following conditions? What's the frequency of the rotor current under the following conditions? Well, now that I have the synchronous speed, I'm going to use the slip equation that says that slip is equal to 1,200 synchronous minus the rotor speed. Well, at standstill, that's going to be 0 divided by 1,200, which gives us a slip of 1. Okay? So if I know that, then I can go to this equation, 13.3 here. Okay? And I know that the frequency of the voltage and the current that in the rotor are 1 for the slip times the frequency of the source. And then at startup, it's going to be exactly the same at locked rotor or at motor startup. Okay, now part B of this problem says when the motor turns in the same direction as the field, the motor speed is positive. Okay, so part B says the motor's turning at 500 RPMs in the same direction as the field. So again, you know, the synchronous speed is the speed of the magnetic field, and that is always going to be this. Okay, and unless we change this frequency, that speed is going to remain constant. And for this particular example, it's 500 RPMs. Now, when he says the motor is turning, he's really saying the rotor is turning, right? Because that's what physically turns, of course, is the rotor portion of this thing. So now we can work on part B here a little bit. This is part B. And so the first thing that we're going to come up with is the slip. It's a new condition. It's N sub S minus N divided by N sub S, which is 1,200 minus 500 divided by 1,200, which is going to give us 700 on top. 700 divided by 1,200 are 0.583 or 58.3%. Okay, so that is the new slip that we work with. The frequency, which is going to be this equation 13.3, the frequency in the rotor, does he say F2? Yes, F2 is going to be this slip, 0.583, times the frequency of the source, which for us is 60, and multiplying that out, we're going to get 0.583 times 60, and we're going to get 35 hertz. Okay, so in here, what's going on? These are the conditions that we're looking at here, right? The voltage and the current frequency in the rotor are going to be at 35 hertz based on the motor slip that we're dealing with. Okay? This is a great problem. It goes through all the possibilities with this. Okay? Part C says when the motor turns in the opposite direction to the field, the motor speed is negative. And so the slip's going to change a little bit, right? Actually, a lot of bit. So again, slip, N sub S minus N divided by N sub S. I'll go out here, 1,200, that hasn't changed. And now the motor speed is negative, so it's minus a negative 500. Okay, and this is still 1200. So now we have 1700 on the numerator and 1200 on the denominator. Now we'll see several examples of things like this. You know, we're not limited by any particular stipulations in terms of, you know, this isn't, you know, something we can't exceed. And you know, so in the sense that, you know, using it in the fraction like this. But anyway, I don't really know what I'm saying with that, but what I'm saying is, I'm trying to say the slip can be greater than 1. Okay, so when the slip is greater than 1, like here, the motor is actually operating as a brake. Okay, so what that would mean is, and we'll go into these terms of dynamic braking and so forth and so on, but the motor going in the opposite direction is actually causing the motor to work as a brake. And the frequency that would be applied here would be 1.147 times 60, or 85 hertz. Okay? And then the last one, it says D. It says the motor speed is 2000 in the same direction. Okay, again, excuse me, we don't need to calculate that. We already know that, right? So we're calculating slip. It's 1200. It's in the same direction as the rotor. The motor speed is positive, turning in the same direction. So it's 1200 minus 2000 divided by 1200 minus 800 over 1200. And that is going to come out to negative 0.0667. Whenever we have a negative slip, the motor is actually operating as a generator. Okay, so that means we're actually returning energy back. And the frequency of this new situation is minus 0.667 times 60, or minus 40 hertz. Negative frequency means that the phase sequence of the voltages induced in the rotor is reversed. You know that situation where we talked about a reversal? Okay. Thus, if the sequence was ABC when the frequency is positive, the phase sequence ACB when the frequency is negative, as far as a frequency meter is concerned, a negative frequency gives the same reading as a positive frequency. Now, you might say, how could this happen? Well, you know, and again, we're talking about the frequency of the rotor here. And I'll give you a good example. A good example of when a motor begins to operate as a generator is in a hybrid vehicle, for instance, when you're actually moving, you're taking advantage of motion to return energy to the system. And so you can see this motor that you had been powering before, now it's returning energy back to the system, okay? And it works as a generator. And we'll go into more detail about that later, but I just wanted you to catch the 4 conditions that we have, okay? And again, those 4 conditions that we work with is locked rotor, where the slip is 1. Here we have it in the same direction, and we're going to have some frequency in the rotor that's less than the source. We've got it going in the opposite direction, and when that happens, when it's going in the opposite direction, greater than 1, then it's operating as a brake, and here it's operating as a generator. All right, so that stretched out to be pretty long. I'm going to stop now.